This is Virtual Precalculus, Section 8.4, Part 2. Okay, we're going to work through an example of creating a model for some simple harmonic motion. I hope you had a chance to play around with those mass on a spring simulations. So while we're talking about this, I'd like you to keep that in mind. In fact, you might want to just have one of those open so you can sort of help visualize what's going on here. So this is similar to example 3 in your book, but it's different. It's more challenging. I feel like example 3 is too easy. You can work through that yourself. In this example that I made up, it's pretty similar. We're going to start a mass on a spring oscillating, but we're going to start by pulling it down 4 centimeters below its equilibrium, and we're just going to let it go. We're not going to push it. And we notice that after 2 seconds, it is 2 centimeters above its equilibrium position. Alright, so we're going to try to build this model up. That's going to mean that we're going to need to know eventually values for A, B, C, and D. Right, now D is, I think, the easiest one. D is almost always going to be 0. Unless there's some statement somewhere that the equilibrium position itself needs to be something besides 0, then we're going to make D 0. If they said, alright, the thing moves in such and such a way about an equilibrium position which is 4 centimeters above the floor or something like that, and we were supposed to describe a function that represents the height above the floor, then we might have to put D to be something besides 0. But unless that happens, D is going to be 0, and so right away D is 0. Okay? What about A? A is also pretty easy. The amplitude of this oscillation. Okay, looking at the information there, it goes 4 centimeters above and 4 centimeters below its equilibrium position. That means A is good old 4 centimeters. Okay? So our function for the height as a function of time is already starting to take shape. The sign of, now comes the hard part. How do we find B? B is like the frequency, right? Well, if you look back at the information, there's some time information in there. After 2 seconds, it's 4 centimeters above. Now, what does that mean? It started 4 centimeters below. At some point, it must have passed through equilibrium, and now it's 4 centimeters above 2 seconds later. How long do you think it's going to take for this thing to return to where it started, hence completing one period? Well, you're right. It's a symmetric situation. It's going to take 2 more seconds. Okay? So that means that 2 seconds plus 2 seconds, the period of this thing has got to be 4 seconds. So if we know the period, we can always find the frequency by dividing 2 pi over the period. Okay? 2 pi over 4, because a 4-second period. B has got to be pi over 2. Now, probably the hardest one of all, at least for me, is C. C is something like the phase shift. Alright, now if we just leave C as 0, so if we just pretend that this is done, okay, that's wrong, but what would happen? What would this graph look like? Where does sine like to start? Does sine start at a maximum, a minimum, an ascending node, or a descending node? Yeah, sine starts at an ascending node, going up through equilibrium, right? On its way up. But that's not how we started this. This thing starts at a minimum, right? We start at 4 centimeters below its equilibrium, and we let it go. It goes up and down and up and down like that. So we don't want to start here. We want to start a quarter cycle earlier. Okay, we need to shift this thing to the right by a quarter cycle. If the period is 2, if the period is 4 seconds, then the KPS is 1 second. That's how much we want to shift it to the right. Okay, to the right means we have to put a minus there. And we can't just put a 1, okay? Because, as you know from previous section, the phase shift is actually negative C over B. Right? That's not what we want. We don't want it to I mean, that ends up being what? 2 over pi? That's not the phase shift we want. We want a phase shift of 1 to the right. So we either have to say, look, negative c over b is 1, and solve, and we know what b is. Negative c over pi over 2 is 1, and we can solve for c that way. Or, the way I like to do it is, as I always do, factor out the frequency. We know it's going to be minus. And if you factor out the frequency, it's just t minus 1. Like, we want to shift it to the right by 1. We just put a minus 1 in there to shift it to the right by 1. And then if we don't like this, we can always multiply through, distribute that pi over 2 multiplication. Well, we're only going to have one set of brackets now, so we don't need the square ones. Okay, voila, there it is. All right, either way, you should get this for a value of c. Okay, and then other things your book might ask you to do is graph this, and you guys know how to do that. You've done that a lot. They might ask you, well, how high will this thing be after, I don't know, 1.3 seconds? And all you do is plug in 1.3 for t, right? This becomes 1.3. It's going to be something you want your calculator for. If you want to try this and check your answer against mine, you should get 1.82 centimeters. The fact that it's positive means that we're above equilibrium. Another thing they might ask you is, at what time is this thing 1 centimeter above equilibrium? Okay? And in that situation, what they're asking for is for you to solve this equation. The height, h, is 1, and we don't know t. We can graph this and see where they intersect, and that's a fine way to solve this. Or we can divide by 4, take the inverse sign, and unravel this for t, and that's also a fine way to do it.